In this presentation, we're going to look at compound Poisson distributions and compound Poisson variables. Let n be the random variable that describes the number of claims that an insurer receives per month for one of its claim portfolios. Okay, so it's essentially n is a conventional Poisson variable. We assume that n has a Poisson distribution with the expected value of n equal to 50. Okay. The amounts xi of each claim in the portfolio is normally distributed with mean mu 1000 equals 1000 and variance sigma squared equals 200 squared. Okay. The total amount of all claims received during the period of 1 month is the sum. Here S is the sum, by the way. In other things it usually means standard deviation, but here it means the sum of the total. It's the sum of all the claims, so it could be 400 plus 1,500 and so on. Add them all up, okay? So it's the sum of all of the n claims. Now the thing about this is we don't know what n is, and from month to month it can vary. So there might be 90 claims in 1 month, or well, actually, sorry, the expected value is up here. So let's say it could be 40 claims in 1 month and then 55 in the next month and so on. Okay? So with s equal to 0 for n equal to 0, that's just a sort of little caveat. Okay, and we assume that everything's all independent of each other. So the two questions are specify the type of the distribution of s and then calculate the mean and standard deviation of s. Now, implicitly, because obviously I just told you the name of this, this is the compound Poisson distribution, and that's the definition of it there. Okay. So it's just a bit of a theory and so on about it. Now, it doesn't necessarily, there's compound distributions and compound Poisson distributions. So just actually when there's a compound Poisson distribution, there's a couple of extra things that you could use there. For example, the expected value and the variance. Okay. Now, so, yeah. So the first thing is actually state the answer there. S is characterized by the compound Poisson distribution. You might be able to sort of put in a little bit extra there if you have time, just to sort of something along these lines there, explain why it sort of fits in with that description there, this scenario. Okay? But I won't dwell on that. The second part is actually asking for the expected value of the compound Poisson distribution and the variance. Now, actually, I just sort of gave them there before, here, and in many instances, you'll be actually probably able to just to sort of state them explicitly. Okay. By the way, here, this is a general theory. So here, what we're going to do is replace, here, using general notation, x, y, and n. So essentially what we're going to do here is just replace y with s for this our scenario. Otherwise, x and n are the same. They're denoting the same things. So anyway, so the expected value is straightforward enough. Now that is a little bit of theory there about it. Okay. And just actually, this is a sort of useful little result on how to deal with these conditional expectations, because we're going to use them with the variance and so on as well. But anyway, in a nutshell, the expected value of x, or s, is the expected value of n, which is 50, times the expected value of x, which is equal to 1000. So we expect the total to be, the expected value of s to be 50,000. Okay. Now, just something to remember in general, because it's going to get used here shortly. I'm going to talk about how to calculate the variance in a bit more detail than we're asked. But just something to remember always is the law of total variance. It's a handy thing to remember. You can invoke it quite often without, in these sort of definitions and derivations, you might be able to use it, and you can sort of bring it into your answer without having to justify it, because it's usually considered as take this as known. Obviously, unless the question is derive the total law of the law of total variance. It's also known as the variance decomposition formula. Okay. Now, the variance of S is basically we're starting off with this. Okay. The variance of S is using the law of total variance to sort of rewrite it as follows. Okay. Now, the variance of S given n. This is how we sort of can rewrite these conditional variances here in the conditional expectation. Okay. And so essentially what we can do here is rewrite the expected value of the variance of S given n as the expected value of n given times the variance of x. This seems like a big jump here to go from this here to this, but actually it's not. If you just sort of think about it using a few sort of examples, it's very straightforward. It looks like, you know, one can be rewritten as the other. If you use some sort of real values there, like I was doing up here previously with, and I left it there. But if you use some real world numbers, it starts to click in very quickly. Okay. So essentially, what we can do is rewrite this entire formula as follows. Okay, like this here. Okay. Now, and then we can just sort of expand it out a little bit further till we have the expected value of n times the variance of x times the expected value of x to be squared times the variance of n. Now, recalling that this is a Poisson distribution, the expected value of x is equal to, n. The expected value of n is equal to the variance of n. Essentially, what we could do is decompose it into a product of the expected value of n times that there. So essentially this becomes the expected value of n, or we can rewrite it as follows. So essentially we just factor it out. So the variance of s is the expected value of n times the variance of x plus the expected value of x to be squared. Okay. So essentially what we're doing here is, well, we're picking up here essentially, and we're just putting in our numbers. 200 squared plus 1000 squared. Okay, we were given them previously, and yeah, 50 times that. So overall the variance of s is 52 million, and therefore the standard deviation is the square root of the variance, and that is the square root of 52 million, which is 7,211.10. Okay. Okay, we'll leave it there.